In this video, we're going to derive the formula used to evaluate a double integral in polar form. First, let's recall that we have some conversion formulas that will come into play. Based on our understanding of trigonometry, we know that x is equal to r cosine theta, y is equal to r sine theta, and x squared plus y squared is equal to r squared. And when we convert an integrand from rectangular to polar form, we might be using any one of these substitution formulas. Another substitution formula that sometimes comes into play is inverse tangent of y over x is equal to angle theta. Let's consider this region in two-dimensional space, and this dark blue highlighted region is what we can call a polar rectangle. In order to sweep out this space, we start with the theta value alpha, and our outermost wall is created by the theta value beta. Remember, r is the distance that a point is away from the origin, so we'll say this inner wall here is determined by r is equal to a, and this outer wall is determined by r is equal to b. So let's slide that down here just to get it out of the way. Now we're going to bust this region up into infinitely many different tiny polar rectangles. And to do that, let's sweep out an angle where we've got a theta value and then let's say theta sub j minus 1. And the angle inside here that has been swept out, we'll say, is a small change in theta. We also need to consider a small change in r, so let's consider this band to be determined by r sub I and r sub I minus 1. And the width of this band is a small change in r. Now we're going to take a close look at this tiny polar rectangle here in the center. And let's call this Rij, where Rij is a tiny polar rectangle. And what we're going to do now is try to find delta A, which is going to be the area of that tiny polar rectangle. So let's recall that the area of a sector is given by 1/2 r squared theta, and it is important that theta is measured in radians for this formula. So in order to find the area of our tiny rectangle, what we're going to do is take the area of this large sector and then subtract from that the area of this smaller sector. And when we subtract those two things, the area that remains will be the area of Rij. So the area of this larger sector is 1/2 r sub I squared, and the angle that's being swept out is delta theta. And then from that, we're going to subtract the area of this smaller sector, which is 1/2 r sub I minus 1 squared with the same angle delta theta. So now let's work with this formula algebraically by factoring out the 1/2 delta theta from both terms to get r sub I squared minus r sub I minus 1 squared. And we'll notice that that's the difference of squares, which can be factored into r sub I minus r sub I minus 1 times r sub I plus r sub I minus 1. And if we'll remember from our drawing, r sub I minus r sub I minus 1 is that small change in r. So this can then be rewritten in this form, and now we notice that this is the same thing as a midpoint formula. And let's let r sub I star be the midpoint in our little tiny polar rectangle. So now we have delta A is equal to the midpoint times delta r delta theta. So let's come back up here to our concept drawing and see that the midpoint of the r values is here in the center of our polar rectangle, and it's perfectly fine for us to use that r value as our representative that gets plugged into the surface function. Remember, when we're calculating this double integral to give us the volume between a ceiling function and a region in the domain, we need a domain element in order to be able to plug it into the surface function and determine the overall height of this solid. And so choosing that midpoint is perfectly fine. And as a matter of fact, once we have infinitely many different polar rectangles, the function values begin to look the same no matter what point we use. So this is the area of our small polar rectangle, and the volume of a cylinder is the area of the base times the height. So in order to get this total volume, we're going to add up infinitely many different polar rectangles, first sweeping through in the direction of theta and also in the direction of r, which means that we're going to need a double integral to add up those rectangles in both directions. Now the ceiling function is what gives us the height, and the ceiling function we have described in the past using rectangular coordinates, but now we're going to substitute r cos theta and r sine theta in for the x's and the y's. So our ceiling function is then f evaluated at r cos theta and r sine theta, and our dA is going to be determined by this quantity. So what we'll see in our integrand is that when we convert from rectangular coordinates to polar coordinates, we pick up a factor of r. And then we'll integrate either with respect to r first and then with respect to theta, or with respect to theta first and then with respect to r. In order to find the order of integration, let's take a look at a couple of different domain options. In this scenario, the theta value alpha and beta that stop and start this region are constant values. But the distance that our points are from the origin, the r values, these values are changing. Let's say that this lower boundary of the r values is some changing quantity. R1 is equal to some function of theta. And this upper boundary up here is also going to be some function of theta. And this is a scenario where we will need to integrate with respect to r first. If we envision this small rectangle, we'd see that we can't really integrate with respect to theta first, sweeping in the direction of theta, because when the polar rectangle is up here, the limits are going to be different than they would be if that polar rectangle were up here, or even down in here. So we'd want to add up those rectangles in the direction of r first, because no matter where we are in this domain region, the lower limit and the upper limit are going to be the same. So we'd set up our integrand to be a ceiling function that depends on r and theta. Then we have that factor of r that's needed to get me into polar coordinates. And we said that we wanted to integrate with respect to r first and then with respect to theta. And the r limits would be going from g1 to g2, and theta would be going from alpha to beta. Notice that these innermost limits could contain a theta, and that's okay when we're integrating with respect to r, because in that first iteration, theta is held constant. Let's consider a region that looks like this. This time we have an r value that's a constant quantity giving us this lower boundary. Let's say r is equal to a, and r is equal to another constant value, b, giving us this upper boundary. And here our side walls are changing quantities. So let's call this lower changing side wall theta 1, that is a function of r, and this upper one, theta 2, also a function of r. When we have a region that looks like this, we're going to need to integrate with respect to theta first. Now let's think about our floating rectangle in this region. If we were to go with respect to r first, we would end up with different upper and lower limits depending on where our theta rectangle is located in the region. But if we integrate with respect to theta first, sweeping in that theta direction, we end up with the same lower and upper limit throughout the region, no matter where our rectangle is located. So in this scenario, we would be integrating this function. This factor of r is necessary to get the area of a polar rectangle. We'll integrate with respect to theta first, and then with respect to r. The theta limits can contain a function of r because r is constant in that first iteration, and then the r limits would be going from a to b.